All right, welcome back to probability, this time part 2. And we're going to start off talking about independence and actually non-independence and how that relates to this idea of conditional probability. So here is the formula of conditional probability. And this strange symbol of a vertical line that is called given, and this statement is the probability of B given that A has already occurred. So with independent events that we talked about exclusively last time, like flipping coins and rolling dice, history doesn't matter. If the first 10 coin flips are heads, then the 11th coin flip still has the same chance of heads and tails. History doesn't change probability at all. However, if you're playing cards and you take 10 cards out of the deck, then there's 10 less cards. That's obviously going to change the chance of what happens next. And so when you have to consider history or previous occurrences, then this is the definition you have to use. Okay, and again, with independent events like rolling dice and flipping coins, then history is not important. Probability of B given that A has happened is the same probability of B that it was before. Okay, so let's use this in the rich and famous problem. There's the Venn diagram again, so you can remember what it was like. The probability of somebody being rich given that they are famous. Well, let's throw that into the formula and see what we get. It's rich and famous divided by famous. You always divide by the given part. Whatever the given statement is, that's always going to be what you divide by. So the probability of rich and famous, that's the center of the Venn diagram. That's 0.03. Famous is the entire circle, which is 0.05, with a probability then of 0.6, 60% chance. Okay, so I want to say a couple things about this. The probability of rich is 15%. However, if you are famous, the probability of being rich is 60%. All right, that's much different. So clearly, being famous will change your probability of being rich. They're definitely not independent. Right? Knowing that somebody is famous clearly changes the probability of being rich. But there's another way of saying that as well. It's because they don't multiply. So if two things are independent, their probabilities multiply. It works the other way as well. If they don't multiply, that means they aren't independent. So the probability of rich times the probability of being famous, 0.15 times 0.05 is 0.0075. And that's not 0.03, which is given in the problem. So because they don't multiply, that also means they are not independent. So two ways of saying the same thing. Rich and famous are not independent. Okay, we don't need the Venn diagram. We can make a table called the joint distribution. It has all the same numbers that the Venn diagram did. The 3%, 2%, 12, 83% are neither. But it also has row and column totals. Now these numbers are called the marginal distributions, and they are useful. They are technically in the Venn diagram, but you kind of have to think about the entire area of each circle, because the probability of famous is 5%. That's the total area of that circle. But here it's represented as a nice column total. So this is just another way that we can write the numbers. Sometimes this might be an easier way to approach a problem. So let's consider this table of 500 students. Some of them snore, some of them don't. They study 3 different topics: art, law, and math. So let's ask some questions about these students. So let's first ask, what is the probability of a randomly chosen student snoring? So out of all the 500 students, I'm going to focus on the marginal distribution of snoring, which is that column total right there. So out of 500 students, 320 snore, and that simplifies down to 16 out of 25. Okay, so that's a marginal distribution. That's the total number of students and the total number of snoring students. A conditional probability like this, so given that the student is in art, so given they're in art, I'm going to focus then entirely on just the art students. Out of the 100 art students, 60 of them snore, so that's a probability of 3 out of 5. And the probability the student studies math, given that they don't snore, so I'm going to focus entirely on the students that don't snore. And out of 180 total students, 85 do math. Simplifies down to 17 out of 36. So this is another way that we can kind of see what's going on. When you do the given statement, it's like you are focusing entirely on just those people and ignoring the rest and doing the regular probability from there. Okay, so conditional probability is a way to incorporate some other event or some kind of history that goes along with that. This is going to be useful as when we do trees as well. So trees, we're going to talk about this next. This is a very flexible, very powerful way of doing questions. So here's all the rules. When I say a branching, I'm referring to when the tree splits into different lines, and those lines are called branches. And basically the two important rules are that you write probabilities on branches, and then you multiply branches together to get a sequence of events. All right, let's do a nice, easy example to start with to see how it works. This is rolling 2 dice. And I want the probability that both dice are a 6. Now, this is actually quite easy. You could do this by doing the techniques from the previous video, and they might even be faster. You could look at the table of all 36 outcomes and see how many are both 6. Or you could use the fact that they're independent and use the word and. But I'm going to use a tree here, do it slightly differently. So the first roll has 2 possible outcomes that are relevant to this case. Even though when you roll a die, there's 6 possible outcomes, you want to simplify to the outcomes that matter to this question. In this question, there's only 2 things that matter, 6 and not 6. So I'm going to simplify to just those 2 things. And they have these probabilities, 1 out of 6 and 5 out of 6. That's the first roll. The second roll is a new branching. And you could have 2 possible outcomes, 6 or not 6. And it's the same probabilities because they're independent. All right, so the probability of getting a 6 and then a 6, multiply the branches together, and you get 1 out of 36. And this is actually the answer to the question that I asked, that both numbers are a 6. That's 6 and 6. But I'm going to do the other branches as well just to make a complete tree. So the chance of 6 and then not 6 is 5 out of 36 after you multiply. The probability of not 6 and then 6 multiplied together is 5 out of 36. And the chance of a not 6 and then a not 6 is 25 out of 36. Okay, and that's the complete tree. So I want to say some things about this tree. There are 4 paths through that tree, and they all represent mutually exclusive, unique combinations of events. Because they're mutually exclusive, the probabilities will add up to 1. And if you are considering an event that covers different multiple paths, you can just simply add them up. So for example, if I asked for the probability of getting at least 1 6, there were 3 paths that have that happen. The first, second, and third path had at least 1 6 in them. So I can simply add up those probabilities to get 11 out of 36, and that is the probability of getting at least 1 6. You'd see the same thing if you looked at the table, but this is how you can do it with a tree. Okay, so the next question is a classic. You have a jar with 9 balls in it. 3 are red and 6 are white, and you're going to pull out 2 balls. Okay, and you're going to pull them out without replacement. So the first ball, 2 possible outcomes, red or white. There's 9 balls, 3 of them are red, 6 of them are white. Those are the probabilities. And the second ball, when you pull out, is going to be either red or white. So you have your 2 possible outcomes. But now you have to consider history. If the first ball is red, there's going to be 8 balls left, and only 2 red left and 6 white left. So those are the probabilities if the first ball is red. If the first ball is white, however, then there's going to be 8 balls, 3 of them are red, and 5 are white, if the first one was a white. So multiplying down each path, the chance of red and red is 1 in 12. The chance of red then white is 3 in 12. The chance of white then red is 3 in 12. And the chance of white then white is 5 in 12. I didn't simplify all the way down so you can clearly see they all add up to 1. And now that the tree is drawn, I'm going to ask a few questions. So you might want to take a mental picture of this so that when I do the questions on the next slide, you could remember what it looks like. All right. I want to ask the probability that both balls are the same color. Well, there's 2 ways that can happen, red and red or white and white. So you add up the 2 probabilities, the 2 different paths where the both balls are the same color, and you get 1/2. Probability that at least 1 ball is white. Well, there's 3 ways that can happen, and it's everything except the first path. It's all the other 3 paths have at least 1 white ball, and you add them up, probability is 11 and 12. Probability that the second ball is white, that's the second path or the 4th path, and they add up to 8 out of 12 or 2 and 3. All right, so trees are extremely flexible and useful. If history matters, you can make it matter. If the events are independent, then you can just write down the probabilities, ignoring the past. But trees work either way, and you multiply down the branches to find each sequence of events, and they are all going to be mutually exclusive in the end. Okay. Well, that's the end of this video, and you have all the basic techniques of probability that you're going to need for this class, so I'll see you then. All right.